So, sorry. In this introductory lecture, I'd like to talk about the basics of Schubert calculus. So, the title is Introduction to Schubert calculus. I am by no means an expert. I'm still studying Schubert calculus. So I want to study Schubert calculus all together. I don't assume Schubert calculus is one branch of algebraic geometry. However, I don't assume any knowledge about algebraic geometry. So don't worry. The plan of my talk is first I briefly review the history of Schubert calculus. Section 3, we describe cohomology of Grassmannian. Part 1. In section 4, we introduce Schubert polynomials. Schubert polynomials are closely related to the cohomology of the Grassmannian. In the final section, I will give the complete description of the cohomology ring of the Grassmannian. Cohomology of the Grassmannian. And basic references, comprehensive references. William Fulton, Young Tableau, especially in part 3 of this book, part 3 geometry, and also Roland Maribel, symmetric functions, Schubert polynomials, and degeneracy loci. Especially chapter 3. Okay. Books.
They are all books?
Yes, they are all books. So in section 1, history of Schubert calculus. The so-called Schubert calculus has its origin in the work of Hermann Schubert, not Franz Schubert, Hermann Schubert, in his study of the enumerative geometry. So in 1879, Hermann Schubert published the calculus they are up the random geometry. He studies the enumerative geometry. Enumerative geometry deals with finding the numbers, find the number of points, lines, planes, and so on, satisfying certain geometric condition. So, let me give you a typical enumerative problem. Question. Well, for example, how many lines in a 3 projective space P3 intersect 4 given lines in general position. How many lines in P3 project space intersect 4 given lines in general position? This is a typical enumerative problem. Please think about it. There are 4 lines in general position. So, Schubert's argument is as follows. First, he considers the cases when the Schubert's argument as follows. First, he considers the cases when first 2 lines intersect and second 2 lines also intersect. Schubert first considered the case. In this case, obviously there is one line joining these 2 points. And there is another line which intersects these 4 lines. First 2 lines span a plane. The second 2 lines also span a plane. These 2 planes intersect. And the intersection is also one line. So in this case, the answer is 2. And then Schubert relied on his principle of conservation of number. So then he even if we move these two lines slightly, the situation does not change drastically. So the answer is still 2. So answer 2. So Schubert's argument relies on the principle of conservation of number, but it is very intuitive. So in 1902, David Hilbert requested to give the rigorous foundation of the Schubert calculus. So, problem 15, rigorous foundation. Schubert's enumerative geometry. Problem 15, rigorous foundation of Schubert enumerative geometry. Since then, many mathematicians, especially algebraic geometer, tried to justify his Schubert's arguments. They established the intersection theory. So I will show the relationship between enumerative geometry, Schubert, algebraic geometry. The algebraic geometer established the intersection theory. For example, Hodge, Kleiman, William Fulton, contributed to the intersection theory. And on the other hand, in a naive sense, a subvariety of a variety determine the cohomology class. Around 1930, the cohomology theory was developed, and in a naive sense, a subvariety of a variety determines cohomology class, and the intersection of two subvarieties correspond to the couple product. So, in modern language, in topological language, intersection theory translated into the cohomology theory. So, topology. In the topological side, first, cell decomposition of homogeneous spaces was given by Ellsman, Charles Ellsman, Chan, Claude Schubert. And cohomology of homogeneous species was studied by Alman Borel or Raoul Bott. And and the Schubert calculus is also related to the representation theory. Representation theory. Representation of the general linear group or representation of the symmetric group. They are studied by Issei Schubert and Weil, Hermann Weil, and so on. As I explain later, the Schubert polynomials appear as the character of this representation. They are related. Then also, combinatorics. Many combinatorialists are interested in Schubert calculus. Studied Schubert calculus. For example, Alan Lascu, and Marcel Schutzenberg. Schubert. They discovered the so-called Schubert polynomial. Schubert polynomials are generalization of the Schubert polynomial, in a sense, which was discovered by Alan Lascu and Marcel Schutzenberg. In 1982. Since then, many combinatorialists studied Schubert polynomials. So they are related. And another special feature of Schubert calculus was relation in with quantum cohomology. Quantum cohomology was constructed by physicists around 90 and by physicists. It turns out that they are closely related to enumerative geometry, Schubert calculus. So many algebraic geometers studied quantum cohomology. For example, Aaron Bartram, William Fulton, and so given Tar Kim. This quantum cohomology is the most active research area in these days. So now Schubert calculus is various related to various research areas. So in this lecture, I will introduce the basics of Schubert calculus. Section 2. In this section, I will introduce the main object, main player in this lecture, the complex Grassmannian. Definition of the Grassmannian. Definition. For the integer, the complex Grassmannian. In the Schubert calculus, complex Grassmannian denoted by like this, or sometimes Grassmann, or various notation. In this lecture, we denote GRU array. It's a set of r-dimensional subspaces. Which is a complex Grassmannian. The complex Grassmannian has a lot of presentation. For example, another presentation. Let EI be a standard basis. Let V be an element of Grassmannian. And V1 to VR a basis of Vとwhere each Vj is column vector A1j A2j AMJ that is Vj equal Aij Ei. These vectors determines m by m times r matrix of rank R. M times R. So the element of the Grassmannian V determines M times R matrix of rank R, and conversely the columns of two matrix E of rank R determine generate the same plane if and only if there exists an invertible matrices such that therefore we have another presentation definition. Grassmannian is represented by M times R matrix rank equal to R divided by the GLRC action, right action. And also, the Grassmannian is represented as a homogeneous space, which I'll explain. GLMC acts transitively on Grassmannian. The stabilizer, isotropy subgroup stabilizer, of the space FR. FR denote subspace, R-dimensional subspace spanned by E1 to ER. This the following matrices. One of the parabolic subgroup. So we can define the Grassmannian as a homogeneous space. GLMC over parabolic. Also, a unitary group acts transitively on Grassmannian. So, Grassmannian is represented as a homogeneous space of unitary group. The first presentation shows that Grassmannian is complex manifold, complex dimension, R times R n minus R. The second presentation shows that the Grassmannian is differentiable, compact, differential manifold of dimension R n minus R. This is a complex Grassmannian. And I want to mention another special feature of the Grassmannian. The complex Grassmannian is non-singular projective variety. Non-singular projective variety of complex dimension. The explicit embedding is given by the Brücke embedding. Brücke embedding. Brücke embedding is defined by projectivization of the exterior power, exterior product. the definition is since V is r-dimensional, R's exterior is one-dimensional, so which determines a line in this vector space. This is Bruch-Eimeling. So through this Bruch-Eimeling, Grassmannia is becomes a projective variety. Note, Grassmannia can be considered as the set of lines, set of r minus 1 planes in the projective space, planes of sometimes we think Grassmannian as a set of r-1 planes of Pn-1. In later sections, we solve the question 1-1, as I mentioned. When we solve the question 1-1, we think Grassmannian as the set of r-1 planes of Pn-1. This is a complex Grassmannia. We are interested in the combinatorial aspects of the cohomology of the Grassmannia. So before describing the cohomology, I will prepare some notation about combinatorics. Combinatorics. Basic references. McDonald. Symmetric functions. And whole polynomials. First, I will introduce partition. A partition is usually denoted by Greek letter lambda u. The non-increasing sequence of non-negative integers. Only finitely non-delta. Non-zero terms. And usually we do not distinguish between two such partitions, 2-1 or 2-1-0 or 0-0. we don't distinguish these partitions. The same partition. It is convenient to not to distinguish. And the non-zero entry is called parts of lambda. And the number of the parts is called length of lambda. Denoted by L lambda. Sum of the parts is denoted by absolute value. This is size or weight of lambda. If the size of lambda is equal to n, we say that lambda is a partition of n. Denoted by lambda n. Note: it is convenient. Another notation. It is convenient to use another notation. Partition lambda is partition, and then my lambda is defined by the number of parts which is equal to a given integer I. Multiplicity of I, called multiplicity. I in lambda. Then lambda is written, sometimes written 1 m1 lambda 2 m2 lambda. This notation is sometimes used. I will give some example. For example, partitions of 4 is
so lambda is 1
1
m lambda?
m lambda 2 m2 lambda.
Lambda as a decreasing.
Yes, so this
it's difficult to write. Yeah, okay.
Usually non-increasing things. However, in this notation, usually so 4 3 1 2 2 2 2 is also denoted by 2 b 2 2 2 1 1 is really. One is 1, 4, 1 to the 4. There are 6 partitions. Next, I will introduce Young diagram. For each partition lambda, there corresponds to some diagram called Young diagram. Partition. There corresponds to the so-called Young diagram. Or sometimes Ferrar's diagram. It is defined by there are lambda 1 boxes, lambda 2, and so on. Lambda. For example, consider the partition of 4. There corresponds to the Young diagram. And we need some notations. Conjugate partition. Conjugate partition is defined I will give you some example. 4, 3, 1. Along the main diagram, convert. So, 3, 3, 2, 2, 1. So conjugate partition is denoted by T. 3, 2, 2, 1. Conjugate of lambda. Conjugate partition is sometimes denoted lambda prime or lambda tilde or lambda star. the lambda mu, two partitions. Lambda contains mu is defined by the diagram of lambda. Contains the diagram of mu. Namely, lambda I is greater than or equal to mu I for any I. Usually we don't distinguish the partitions and the Young diagram. Next, when we deal with convergent Grassmannia, we use a diagram contained in the rectangle. So n times R rectangle. Rectangle is the partition given by R times. So the Young diagram is just R times n rectangle. When lambda is contained in the rectangle, we define
Is it n times r or r times?
rectangle in R times n.
So, and then you write matrix, you usually have r times n.
R times, sorry. R times, sorry. R times, sorry. R times, sorry. R, okay. Sorry. Complement for dual partition is defined by the dual partition or complementary partition. Or complementary partition is defined by the Young diagram of the dual partition is just the complement. So R plus 1 minus I equals N. This is a dual partition.